Yes.
Okay, so I would want to start from here. I mean, this was pulled from 5 different data dictionaries. And this one, for example, had about 600 different data elements. This one had slightly above 100. This, I really can't tell this because there was a lot of curation and trying to redefine things. And this was maybe about 28 or so, 29. And this about 75 or so. So what has been done here is we had to go through every single one of these data dictionaries and pull out all the data elements or the variables and spread them out on this spreadsheet such that we match the ones that mean the same thing. So I really cannot estimate, but this work took maybe above 50 hours. And till date, I'm not sure it's 100% accurate because there's always room for human error. So imagine therefore that someone has to go through all of these. You can imagine how time consuming and somewhat frustrating the exercise can be, and even annoying when you know that at any point in time, if you really want to go through it, the chances that you find an error are pretty high. So I started with this because this is what motivated me as we work on the grid to prepare this presentation. Hopefully you can still see.
Right now we're seeing the presentations mode.
Are you seeing my PowerPoint slide?
We do see the PowerPoint, but we see the that screen for the people that are presenting that is smaller, has a bunch of annotations.
Okay, let me hide presenter view.
Let's see. Yes, now it's
Okay,
perfect.
cool. Thank you. So this presentation is titled Document Analysis with Python for Data Dictionaries. Just to give a little background. So what I initially showed, the spreadsheet I showed, was one of the early steps towards building what we call the GRID, the Global Repository for Injury Data. I would often liken it to what the Institute of Health Metrics and Evaluation at University of Washington is doing, and also to some extent what University of Vanderbilt University has done with the Red Cap. So the whole idea of the grid is to build a repository for injury data such that we can link up injury data from different countries, and such that should someone want data from a specific number of countries, the person would be able to get just that data. But there are a series of pitfalls, a series of challenges to overcome. The first thing is we understand how different data collection tools are. Even when they mean the same thing, for example, maybe measuring blood pressure as in blood pressure, there will still be variability in the tools that are being used. So by not going too far into that, let's focus a little more on the variability that is just across different instruments. So the way variables are often referred to is different. And if we want to match variables, that would mean that we have to go into each dictionary, and assuming that is properly done, because that would be another difficulty, and then analyze those dictionaries and then try to link the variables together. So what we are going to look at today, we are going to have a quick look on what document analysis is, and then we shall visit natural language processing, and then we shall look at these two very special packages called Spacy and DeepLib, and this one is my favorite. And finally, we shall go to Python and have some fun. So document analysis, as most of us already know, is a research method that has to do with analyzing documents and pulling some form of inference from them. It could be just reading a document and doing a thematic analysis, or it could be comparing two or more documents together. But in this presentation, the document we are talking about would look something like this: a typical simple sample data dictionary where you have the variable, and then we have the class, and then we have a brief description. So the next thing we want to know is what natural language processing, or NLP, is. So it is an artificial intelligence subfield that tries to enable the computer to understand human language and interactions. So there are some key techniques that include text processing, which is the one we are focusing on today, but we also have machine learning and deep learning. So some very common packages that are used for text processing include Spacey, Difflib, TextBlob, and Jensen. And Spacey is kind of open source and free package that is very useful for text processing. And some of the important features of Spacey include the fact that it supports over 75 languages, and it has up to 84 trained pipelines for 25 languages. And then it possesses state-of-the-art speed, and also is linguistically motivated when it does its tokenization. So as it tokenizes, it's kind of motivated by the language power or the linguistics behind the language it's using at that point in time.
Ubali,
Yes.
can you give us some more background on what is the tokenization there that you mentioned?
Yeah, tokenization would just be breaking down. If there's a sentence, for example, this is a boy, the tokenization would mean pulling out every single word of punctuation and then interpreting it and giving its meaning.
Mm-hmm. And why do we need to tokenize the sentences? Do you know?
Well, the machine, I'm not quite sure, I'm still doing some research, but you know, the machine doesn't understand like the human. So it has its own patterns, its ways of making meaning out of human data. Yeah.
Makes sense. Mm-hmm.
So the next one is Difflib. This one is specifically designed for comparison of different documents, and it contains classes and functions for that purpose. It's very, very useful for comparing files. As a matter of fact, many argue that it does better if it's for comparison purposes than Spacey. And Difflib also is inbuilt in Python and really does not need installation, unlike Spacey that needs installation. So there we are done with the slides. We are going to move on to the Jupyter notebook and see what we got. Oops. Please ignore this. Sometimes I can be a bit old-fashioned. Okay, so first we are going to load our packages. We shall load Spacey, which I've already defined, Difflib, and Pandas. Pandas is a library that is used for some mathematical kind of processes. And then since we don't want to see the annoying warnings, we shall suppress them. So we are going to load Spacey, or rather we are going to understand what Spacey basically does. So I will not go into all of this because the idea is not to teach programming here, but the idea is to understand the output and what we seek to make out of it. So when we run this line of code, this is a sentence, this is a sample sentence. The function NLP tokenizes it and breaks it into its various parts. So you see, this is a sample sentence, full stop. So it tells us that this is a pronoun and it is a nominal subject, is auxiliary, and it is a root. A is a determiner, and then sample is a noun compound, and then sentence is also a noun, and while this full stop is a punctuation. So that's what is called tokenization. So the computer kind of understands it that way. So it's interesting. However, this is not the direction we are taking. Our direction is basically to be able to compare two different dictionaries and make sure that these dictionaries, or make sure that whatever we are doing or the algorithms we are using are able to match variables that mean the same thing. So the next thing we want to look at here is how spaCy works. So it does some kind of relating of words. So we are going to use two words here, red and white. And then we shall pull out the vocabulary for each of the words. And then we shall ask spaCy to calculate the similarity between the two words. So we run that, and then we get the similarity. It says the similarity in this case is 66.8%. Should we change this white to red and do the same thing? We now see that the similarity is 100%. It's basically the same word.
And
So
by similarity there about before, when you were comparing the two different colors before, so the 68% means that even though they didn't have the same characters, the same letters, they probably are nouns. They are, their meaning is similar because they are colors. So this is why they are similar.
that's correct.
Okay.
Yes, if we put a different, let's say goat. See, the similarity has significantly dropped. Yeah,
I see.
thank you for pulling that to our attention as well.
Mm-hmm. Nice.
I also have a question there.
Yes.
The way that this is calculated, is there like a weight given to certain components of the comparison? So since this was a noun and it was a color, then each characteristic of the word has a different weight. And is that published, or is there somewhere you can refer to see what has a larger weight?
Well, that would be my guess, and sincerely, I'm not sure.
Okay, perfect.
Yeah. João, do you have any thoughts about this?
I'm sure that for at least the background, they might reference the algorithms that do the comparison, Pamela.
Okay.
I don't know them as well, but I'm pretty sure that, like, since these are like the basics for all of the big models, like the ChatGPTs, the large language model, etc. All of them use this to compare the words as well. I'm sure that they have that published, but I'm not sure how they work.
Okay, perfect. Thank you.
Yeah. Thank you for that one, Pamela. So let's ride on. So at this point, let's get a little serious. And so what we are going to do here is we are simulating two different data sets that are typically the way a simple dictionary would be. So we have data one, which has variable names here, I think 10 in number. And then we have their levels, and we have the description for each one of them. So we are going to run this chunk. And there we go. So we have age, height, weight, gender, income. And then we have the description, age of person, height in centimeters, height in kilograms, weight in kilograms, and so on. And then for the next, and this is why I always prefer R for statistics. See what Python does here is a bit crazy, but I prefer Python for programming anyway. So here we have the second data set. We have person age, which is still the person's age. We have education level, and so on. So we are going to now use Spacie to see whether we can compare the two and then match them together. So this is what the code down there is doing. What it's doing is that it is comparing levels for data 2 with levels for data 1, and then getting similarity for each row, such that for each variable, there are 10 variables in each category, each data set. So for the variable levels, it's going to start with the very first row and then compare it with every row for dataset 2. Take the second row for the first dataset, compare it with every row for dataset 2 for the variable level, and then does the same for the variable description, and then calculates a form of similarity, and then tries to use that similarity and match the variable name. So that, okay, based on what I see, this variable matches very much this one, this other one matches this one, and so on. So that's what the function down here is doing. So it calculates similarity of text 1 and text 2. It says if text 1 is none or text 2 is none, it should just return 0. But if not, it should calculate the similarity just as we did above, and then return the similarity for the documents. So that's the function that has been written, and then we create an empty list that is going to store the similarities. And then here we calculate the similarities for all the pairs of variables as I already described. So this is like the variable similarity. It will calculate similarity for variables, row 1, which is from dataset 1, and row 2, which is from dataset 2. And then it will also do level similarity, and then it will do description similarity. And then to have some average score, is going to sum the similarities and divide by 3. And then it's now going to append this. It's going to append each variable, each pair of variables together with a similarity and save it in this empty list. And since we want to see the top n numbers, where n would be the number of rows of the variable or of the data set with the highest number of rows, we are going to have a kind of similarity sort, and then we'll print it out as a data frame. So we shall run this chunk. It's going to take a bit of time here. Okay, see what it tells us, that gender and person sex have a similarity of 64%. Employment status and employment status person, that education and education level, gender and marital status, marital. So it does that and ranks them, and we have up to 100. Python indexing starts with 0. So we have 100, which makes sense. 10 times 10, if you have to compare each variable with the other, then it should be 100 different comparisons. So now, the next thing is we want to see just the first 10, since we do not want any of the variable pairs to repeat. So we want to ask you, tell us now, according to your findings, which variable is very likely to match which variable. And we run this chunk. And then what do we see here? We see that it says gender is matched to person sex, employment status, that, education level, marital status person, correct. Age now, it says patient's height. That's wrong. And then number of children, household total size, correct? Income, annual income, weight, children number, no. Household size, person's weight, no. Height. So in brief, it has just 5 correctly matched. So I think this takes us back. This confirms the point you made in your question, Pamela. It doesn't have that intelligence to see beyond the way it sees similarity. So it will try to say that this, for example, this height, person's age, it really cannot look beyond what it would look for. Maybe if we had put colors, animals, houses, cars, it would really be able to match them. So, but let's look at what DeepLeap does with the very same data set. So everything is pretty the same. It's just that now we are using DeepLeap and not Spacy. Okay, so here it says employment status and employment status. See now the similarity is very high. Here it gives it up to 82% or 83 to round. And here 80, 74, and so on. Whereas here we have percentages like 64, 57, 58, pretty low. So it seems when it comes to comparison, indeed, Spacy is more intelligent compared to DeepLeap. And then the same thing again, we ask it, so tell us, what do you think? How do we match them together? And it says here that employment status is matched to employment status person, marital status person, education level. So it gets it all 100% correct. Yeah, so with this approach now, if we had applied whatever we did here, we would have used less time and had more accurate results. The only place where the human would come in would be to kind of look through and make sure that everything makes sense, just in case the computer made some error. Of course, which again would be related to the fact that languages are different and the way people would describe or even create data dictionaries would vary. So yes, that's all I had for today. If you have any points, any contributions. So this I have taken to be part of a series. I'm going to continue with this until when we successfully build the grid. So we shall do some research and keep learning and seeing what is going to be useful in building the grid.
That is great, Obale. I feel like, as you said, like for the grid, the tendency is for us to get more and more dictionaries to compare as it gets done, right? Because we hope that more and more countries would like to join our effort and share the data at least. This is a great way of doing this initial filtering, this initial screening of all of that for sure. And I wonder if we could tie this, or at least, as you said, for a second step, to make to suggest harmonization steps. Like with this result, it's saying, for instance, that age and person's age is similar, 82% similar. But if we look at how the age was actually collected, maybe one of the studies collected only in years, and the second study collected in, integers, right? So only whole numbers, versus the second study collecting is at 12.5 years old to 30.2 years old. That's incomplete years as well. So maybe we could have a second step where one of these other algorithms would suggest harmonization between these two sources. At least for age, it comes to mind that, okay, let's transform that into integers for everyone. So let's round it to the lowest, to the closest integer. So I don't know, 12.4 becomes 12 and so on and so forth. But it's going to be more tricky for other types of variables for sure. Like, I don't know, mechanism of injury or where the injury happened, the severity of TBI and all of those stuff can have many, many different categories, and deciding on how to connect them later is also going to be a challenge, right?
Yeah, I totally agree. And I think, Joao, we had discussed this together. So based on the caveats that you are pointing out, the potential caveats that you are pointing out, I think it would be appropriate to kind of merge computer intelligence with human intelligence, as in now build it like in the form of a dashboard, something such that when these algorithms are run, what the computer will do is to ask us a question that, oh, I see a high similarity there. Do you accept that these two match? And then we say yes or no, and just something like that. Yeah, to minimize chances of error.
That would be ideal. I can totally see this integrated with some, some large language model that is safe. I mean, this is just data dictionary, so we could send it to the company. That is no problem. No sensitive data there. We could do something on, okay, so Obale did this work with the 5 countries, and we have this sort of standard format now. So let's take a different countries, or maybe a data coming from a different place in Tanzania, in Brazil, whatever. And what the model is going to do is say, okay, this new data should be harmonized closely related to the categories that we want. And thus it's going to give the suggestions for the person that is doing it. In the past, you have chosen to do A, B, C, and D, but now there's a new category, which is F. Do you want to include this new category? Do you want to do a different thing? I can totally see that happening in the future. And maybe even doing something like, okay, the grid repository is on, but we're going to have a curation, a data curation committee or something, or board, where this has to be approved by the board in a review, and then it gets included to the repository afterwards. Like this states like versions, revisions, so it gets harmonized. I think that's totally possible.
Yeah, absolutely.
Awesome.
Yeah.
I have another question. Oh, sorry.
Go ahead. Sorry. Go ahead.
I'm just curious, even before getting to the step with Python, on how do you get the data sets cleaned, like the data cleaning step in the format ready to be analyzed? Like, do you use R, or what do you do to get it cleaned up and standardize across data sets?
I'm not quite sure if I understand the spirit of that question.
So you know how you had like column A variable, column B description or stuff like that for the variables. So in the data dictionaries, you might have different structures of how the original institutions organize their data set. How does that process look like to get the data sets ready to be compared with each other?
Yeah, I mean, that's one of the caveats that we have to look out for. But what I would strongly recommend that should not be overlooked is the source of this data. So I would generally create a new column that tells us maybe the country or the institution, so that even while you are trying to draw inference across data sets, you now are aware that all of these rules come from this institution. And so this institution may have likely seen things this way. So to relate to this other institution that saw things this way, there may be some need for some kind of, what is this term? Is it text mining or, yeah, I mean, some data engineering kind of stuff, just to make sure that they are kind of adjusted. For example, if you asked me, in Cameroon, we use the franc CFA. If you ask me that how much is a house in Cameroon, I would not tell you the amount in US dollar, or even if I tell you, I would let you know that, but looking at it through the lens of the dollar in the United States, this is what that amount would be. So that's now that some kind of adjusting. For example, tuition in Cameroon would be like 1,200 US dollars. Say, oh, that's so cheap. But to get 1,200 US dollars in Cameroon is like to get 45,000 US dollars in the United States. So that's now some kind of adjustment So that is what I would do to the data to make it really comparable.
Yeah.
Thank you.
Yeah.
And out of this work, Pamela, it's sometimes even before getting access to the data and doing it, we're just working with the documents. For instance, for Obale's case, the grid partners, they agreed to join and to do this effort together. But the idea is that with this repository, they don't need to actually share the actual data with us, at least for this initial step, because we want to keep the ownership, the governance of the data where it is, and doing something that will, at least whenever they need to share for like doing some analysis, doing some tests, it's already gets de-identified, organized, and in a way that they can leverage that in their own institution as well. So beyond aggregating data, we want to try to address this as well with the governance and all of that. It's a lot of things to do, but this is a great effort from Obale and the group for sure.
Perfect. It's like we